All right, everybody, thank you for tuning in and watching this online lecture. So I apologize for not being able to give an in-person lecture today, but with the weather the way it is, we have closed campus. We unfortunately do not have enough time in the schedule for us to just miss a day. So I'm going to record today's lecture and give it to you digitally over YouTube or on Blackboard or in some form. So for today, you were supposed to have read sections 1.3 and 1.4 of the textbook. Before we jump into that, I want to talk a little bit more about the chain rule, because I think there was some confusion around it at the end of class last week. So the chain rule, the one I'm talking about, is just the chain rule for taking derivatives of composite functions. So let's work a quick example here. We jumped straight into the chain rule for integrating, and we didn't do a good example with the chain rule while taking derivatives. So a quick reminder of the chain rule. I guess real quick disclaimer, this is the first time I've ever used a tablet to try and kind of provide lecture notes before, so if my handwriting is horrible, I apologize. But let's see if I can find my mouse. There it is. So the chain rule is for taking the derivative of a composite function. And by a composite function, I mean if you have a function like f of g of x, where f is a function of g and g is a function of x. And if you want to take the derivative of f with respect to x, you use what is called the chain rule. So if I want to take df dx, the chain rule says that that is df dg dg, dg dx. That is what the chain rule says, how you take the derivative of that composite function. So let's work a quick example of something that you've probably all seen before. If I say that y is equal to the sine of x squared, and I ask you to find dy dx of that, everyone in this class has taken so many derivatives that you don't even do it. You don't even have to think about using the chain rule anymore. You do it naturally. But if we're trying to be rigorous, the way you actually take this derivative is you say that you're going to let u be equal to x squared. Then you're going to say that y is equal to the sine of u, and using the chain rule, you would then say that dy dx is equal to the function of sine of u with respect to u, so dy du. So we'd say dy du du dx, which is then going to be, that's equal to sine goes to the cosine of u, and then du dx is just 2x. So we can then say that dy, let's go down to one more line. We would then say that dy dx is equal to 2x cosine of x squared. So you would do that in your head. You would not go through all those steps in order to take that derivative. But if you wanted to be rigorous about it, you would then substitute u is equal to x squared into your function. You would take the derivative with respect to u and then include the derivative of u with respect to x. Okay? So in that same sort of concept, let's work an example here. So in this example, let's say that I have a particle, and it is, let's go down here, I have a particle, and it is moving along an x-axis. Okay, so it is moving along some x-axis. This will be negative x, so it's moving in rectilinear motion like we talked about last week. And let's say that the velocity of this particle, I give you the velocity of this particle is equal to x squared. Something simple. Let's just keep it simple for this case. So what does this mean? So this means that when x is very negative, so very large negative, let's say something like negative 1,000, the velocity is very high, because negative 1,000 times negative 1,000 is 1,000 squared, so a large number, and so it's moving very quickly. So it's moving very quickly, if I mirror image my thing, moving very quickly from the negative x position towards the origin, right? So it moves very quickly, and as it approaches the origin, it gets slower and slower and slower, It reaches the origin, and for just one instant it stops. It has a velocity of 0, and then as it continues on, it starts off slow, and once again its velocity gets larger and larger and larger. So the velocity is always going to be to the right because the x squared makes the velocity always positive, and it's faster the further away from the origin that it is. All right, that kind of makes sense. So if I give you velocity is 2x, and I say, is x squared. So the velocity I've given you as a function of position, not a function of time. And I ask you to find the acceleration. Well, you would say, Zach, that's easy. I know what the acceleration is. It's just the derivative of velocity. So you would say that acceleration is equal to 2x. And that would not be correct, because acceleration is defined to be the derivative of velocity with respect to time, not with respect to position. So what we have done here, so that looks like a D, but that's really supposed to be an A, that acceleration, we've taken that derivative of velocity with respect to position, not with respect of time. So this is incorrect. So what we would need to then do is we need to use the chain rule. So we're going to say, okay, so if acceleration is, I need to pick a pencil. So if acceleration is equal to dv dt, and I have the velocity as a function of position, I would then use the chain rule, and I would say that this is equal to dv dx dx dt. So in this case, x squared is, you think of it as just a variable, but in reality, if this particle is moving, which it has a velocity, so we can safely assume that it's moving, so the position of this particle must be a function with respect to time. So we don't know what that function with respect to time is, but we know it must be a function with respect to time. Now, fortunately for us, we know what this term is. We know what dx dt is. It is defined to be the velocity. So now I can now say that this is equal to dv dx times v, because dx dt is defined to be the velocity. So the derivative of position with respect to time is defined to be the velocity. So now I can then say that the acceleration of this particle, and I can find it as a position or as a function of the position, is going to be dv dx times v. So I can say that it is going to be 2x times x squared, which is equal to 2x cubed. So my acceleration in this case is actually not the derivative of velocity with respect to x. I have to multiply that again by the velocity. So my acceleration as a function of position, I'm able to find as 2x cubed. So now that we've gone the derivative way, hopefully it makes a little bit more sense when we did all the integrals in last class. Okay, so now that we worked a quick example with the chain rule, let's jump into the new material for today. So you were supposed to have read sections 1.3 and 1.4. We will not have a reading quiz today as class was canceled due to weather, but it's good to take a look at the reading quiz and let's just kind of make sure that you understood the concepts that were covered in the reading. So the first question says, an example of motion with a constant acceleration is, and it gives you a bunch of options: a rocket taking off, air drag, charged particle attraction, and a falling object. So the answer to this one would be D. So we know that all objects that are being acted on only by gravity all accelerate at a constant rate of 9.81 meters per second squared, or 32.2 feet per second squared. So a rocket, the acceleration will actually change depending on the mass of the rocket. As the rocket burns more fuel, the rocket becomes lighter and the acceleration increases. Air drag actually depends on the velocity squared, so it is not a constant acceleration. And a charged particle attraction depends on the separation of the two particles over the radius squared. So it actually, the acceleration is not constant because as the particles get closer together, the acceleration increases. Okay, so the second question is, a particle moving in a curved path is generally called curvilinear motion. Curvilinear motion, so we had rectilinear motion was motion for in a straight line, and we covered that last week. Curvilinear motion is the motion that we use for moving within two planes or moving in a 2D kind of problem situation. Okay, so Section 1.3 is line motion, constant acceleration, which was kind of in line with what the quiz was about. So in section 1.3, we are going to be looking at motion when there is constant acceleration. So we know that acceleration is equal to a constant, so we can integrate that and we should have a linear relationship for velocity. And if we integrate a linear relationship, we should end up with a quadratic equation for position. Okay, so our introduction case study is a boy is trying to understand gravity and he holds a ball above the earth and lets it fall. With aspirations of being a rocket scientist, he wonders how fast the ball would fall on other planetary bodies. So what we know is the ball is released from rest 4 foot above the ground on Earth, and the gravitational constant of Earth is 32.2 feet per second squared. So anytime that you have object being acted on only by gravity, we know that the acceleration is constant, but it does depend on the gravitational field in which the problem is taking place. So in this case, the problem is taking place on Earth. We know that the gravitational constant on Earth is 32.2 feet per second squared. I've also given you some constants for some other planetary bodies. For example, on the Moon, the constant acceleration due to gravity is 5.5 feet per second squared, while on Jupiter, it's 75.1 feet per second squared. So, what is the velocity of the ball when it hits the ground? If the ball is being released from rest and is to have a speed of 14 miles per hour when it hits the ground, from what height should it be dropped? So those are the questions we're trying to answer, and our goals for how we're going to answer these questions is we're going to say with the acceleration given as a constant, the velocity and position function can be found by integrating like I mentioned at the beginning of the presentation. So let's jump straight into the theory. So in a lot of problems that will work in dynamics, acceleration will be given as a constant. So since constant acceleration is so common, we will actually derive some equations that are useful for constant acceleration because it's easier to use it instead of having to re-derive those equations for every single problem. Okay, so if acceleration is given to be a constant, in this case we're calling the constant a naught or a sub 0, we're going to integrate that in order to find the velocity function. And we use it, and we do that using the exact same tactics that we learned last week. We are going to use the definite integral strategy in this case. So we are integrating, we know that our acceleration, which is equal to a constant a naught, is equal to dv dt. So we are going to integrate dv is equal to a naught t as shown here, but we are going to take the definite integral. So we're going to integrate from an initial velocity to a final velocity, and then we are going to integrate from an initial time to a final time. But note, because acceleration is constant, we were able to pull it out in front of the integral. We were able to pull it out in front of the integral, and now we can see that this simply becomes that our velocity as a function of time is some initial velocity plus an initial acceleration times a change in time, So we have v naught is plus a naught times t minus t naught. So in this case, we would say that v as a function of t, where v naught is a constant, a naught is a constant, and t naught is a constant. We know what all those values are based off of boundary conditions of the problem. So now we have v as a nice clean function of t. Okay? We can take that same equation and we can apply that same strategy and we can integrate to find the position equation. So once again, dx is equal to v dt. We integrate that from an initial position to some position x. We integrate from some initial time t naught to t of that same equation. We perform that integral and we get our classic position function that you probably saw in physics 1. You definitely saw in physics 1 in kinematics, and we say that x of t is equal to some initial position plus some initial velocity times a change in time plus 1/2 times some acceleration times a change in time squared. So these are our velocity and position equations for constant acceleration. Now you probably remember from kinematics that we had another equation in which we were able to relate velocity and acceleration and position not as an integral of time. And in order to derive this equation, once again, we are going to use the chain rule. So we are going to say that dy dx is equal to dy du times du dx. So this was the kind of definition of the chain rule like we just went over at the beginning of class. And now we're saying that since our acceleration is constant and our acceleration is equal to dv dt, I can use the chain rule on this dv dt just like we have been before and say that this is dv dx times dx dt, which we use that same strategy, dv dx times v. So now I can integrate this relationship. So I multiply my dx out through, and I end up getting v dv is equal to our initial acceleration, or our constant acceleration, dx. And now I can integrate this equation. So I'm integrating once again using the definite integral strategy. So I'm integrating from some initial velocity to a final velocity of dv. And that should be, I apologize, there's a mistake in that. I can fix it. That should be the integral of v dv. We're integrating v dv, and then we're integrating once again some constant acceleration from an initial position to a final position, right? So when I integrate v with respect to dv, or v with respect to v, I get 1/2 v squared. I'm evaluating that at some velocity v and some initial velocity v naught. Once again, my a naught I was able to pull out in front of the integral because it's just a constant, so I get some change in position here. I can now evaluate this at v and v naught. I can multiply both sides of the equation by 2, and you get your standard kind of position, change in position, change in velocity equation for constant acceleration. So, a couple things I want to point out about this particular equation that we need to remember. In this equation, velocity is squared. Velocity is squared, so when you're solving for a final velocity, for instance, you will end up taking a square root. If you take the square root of anything, plus or minus are possible answers for that. So you have to analytically determine the sign of your velocity based off of the problem. So this is a scalar equation, is what we say. It gives you a magnitude of velocity. It does not give you a direction. As opposed to this previous velocity equation here, this previous velocity equation is a scalar equation. I'm sorry, it's a vector equation. It's a vector equation. If you know what your acceleration is, and you know what your initial velocity is, and you define a positive direction, a negative answer would then indicate that your velocity is in the opposite direction. So this equation here will actually give you velocity as a vector. It will give you a direction and a magnitude. This equation right here will only give you a magnitude, and you have to analytically determine the sign of that velocity, so you have to know something about the problem in order to determine the sign. Okay, so that's all the theory for section 1.3. Let's go ahead and jump into the case study. So we said for part A, what is the velocity when the ball hits the ground? And we knew that our initial position, in this case we're calling it y naught, was 4 feet above the ground, and we're saying our final position y is equal to 0. So we defined our datum point as 0 feet is at the ground. Okay, our initial velocity is 0 feet per second because the child just dropped the ball. He didn't throw the ball downward with an initial velocity. So our initial velocity is 0, and our acceleration is a constant negative 32.2 feet per second squared, which is the gravitational acceleration on Earth. Okay, fair enough. So now I can say that I'm looking for the final velocity when the ball hits the ground, and there are 2 different strategies that we can do to solve this problem. So the first strategy we can do is we can say, okay, given the fact that we know what the position equation is, I can figure out what y as a function of t is. I can then determine how long it takes for that ball to fall 4 feet until it hits the ground. I can then use that time, and I can plug it into my velocity equation, and I can determine a velocity. So let's do it that way. So this is our initial position equation with all of our values given, and I'm saying that we know immediately that y naught is equal to 0, v naught is equal to 0, so these first 2 terms disappear. So we're left with really just this last term here, and we know that our final position is also equal to 0. This final position is also equal to 0, so we can say that 1/2 at squared is equal to 0. This y naught is also equal to 0. So I can solve this equation for t squared, and I can say that y naught was given as 4 feet, but we're solving it in general, so we can solve this equation in general for any y naught. And now we can say that t squared is equal to negative 2y naught. It shouldn't be negative. Yeah, it should. Negative 2y naught over a naught. Now I can say that t is then the square root, and I'm plugging in my values for both y naught and a naught here. So I get a negative 2. I have an initial position of 4 feet, and I know that my acceleration due to gravity is negative 32.2 feet per second squared. So I take the square root of that, and I end up getting that the time that it takes for the ball to fall 4 feet and hit the ground is 0.4984 seconds. Okay, so pretty roundabout method, but I'm able to find that time. And now the second step of this method is I then plug this time into my velocity equation. So our velocity equation is that v naught plus a naught times a change in time. So we can say that v naught we know to be 0, a naught we know to be negative 32.2. Our time we've already found, and we define our initial time when the child drops the ball to be 0. So I can just plug all that in. So I can say that velocity as a function of time, so this is time at 0.4984 seconds, is equal to negative 32.2 times 0.4984 seconds, and I get negative 16.05 feet per second squared. So the big takeaway is when we used this method, because we came back to this vector equation here, we ended up with a sign. We ended up with a sign of negative 16.05 feet per second squared. And the way that we defined our axes in the problem, we defined it as y being positive up. So negative 16 then indicates that the velocity is in fact down. So it's a vector equation. We were able to find a magnitude and a direction. Okay, so method 2 to solve this problem is we can use our velocity position equation. If we don't want to go through multiple steps and solve for some time and then plug that time back into a separate velocity equation, we can actually solve it in one step, and we can use our velocity position equation. So our velocity position equation is given v squared is equal to v naught squared plus 2a naught times a change in position. So we can say that the velocity squared on the left side of that equation is the value we're looking for. Once again, our initial velocity is 0, and our acceleration is a constant negative 32.2 feet per second squared. I know that my final position when the ball hits the ground, so just y is 0, and my initial position is 4. So I can plug all these values into this equation. And you'll notice that we end up with a v squared is equal to 257.6. So I can take the square root of that, and I know that my answer, my velocity, must be plus or minus 16.05. Because I take the square root, it can be plus or minus, and now I am responsible for determining the sign of that problem. So we know that if we're dropping a ball, that it should be going downward with the way that we defined our axes. So the correct answer would be negative 16.05 feet per second, but we are responsible for determining that negative sign because this is a scalar, this is a scalar equation. This is a scalar equation. So two different ways to solve this problem. One's 2 steps, but it gives you both magnitude and direction. One is 1 step, but it gives you a scalar answer, which you have to interpret the value of the sign, the direction of the velocity yourself. Okay, the second part of this problem says if the ball is being released from rest and is to have a speed of 14 miles per hour when it hits the ground, from what height should it be dropped? Okay, so this is the same type of problem, but instead of giving you the initial height, I am now giving you the final velocity. So now I'm giving you v and asking you to find y naught, which is really, it's just some algebraic manipulation of the same equations. But I gave you speed as or in the form of 14 miles per hour when our acceleration is negative 32.2 feet per second squared. So whenever we're working problems, all of our units need to match. So we have an acceleration with units of feet in second. So I need to have a velocity with units of feet in second. So I need to convert from 14 miles per hour to feet per second. And I do that by multiplying by 1, clever forms of 1. So I have 14 miles per hour times 5,280 feet per mile. My miles then cancel out. And then I say times 1 hour over 3,600 seconds. That's still a form of 1, but my hours now cancel out. So 14 times 5,280 divided by 3,600. I get that my velocity is 20.53 feet per second. 20.53 feet per second. So once again, you can do this the 2-step method or the 1-step method. In this case, it's a lot easier in order just to use our velocity position equation. So I'm saying that I just determined that our final velocity is 20.53, so I can plug that into our velocity position equation here. Our initial velocity is 0, so I know that that's 0, and I know everything in this equation now, but why not? So I can now solve for y naught, and in order to have that ball hit the ground at 14 miles per hour it needs to be dropped from an elevation of 6.547 feet. 6.547 feet. Okay, so let's move on to 1.4, which is curvilinear motion with rectangular coordinates. So we are no longer working in one-dimensional motion. Now we are stepping it up to two-dimensional motion, which can be a little bit more complicated. Okay, so our introduction or our case study is we have a cargo plane has to drop a relief package to the people in need. How can the pilot determine when to drop the package? So I'm giving you that the plane is flying level and it has a elevation of 600 feet. So it's flying vertically. It has a vertical velocity of 0, so it's only flying horizontal. It has no vertical component of its velocity. It's only horizontal, and it is at a height at 600 feet. Okay, the horizontal velocity I'm then is giving you as 176 feet per second, and it's a straight line towards the drop zone, and the wind resistance we're going to neglect. So we're going to neglect drag, so we're just going to be able to assume that when we drop this package, it falls in standard projectile motion, so it's only being affected by gravity. Okay, so we have a little bit more of a drawing here. So when releasing the package, the question we're asking ourselves is when releasing the package, at what angle theta down from the horizontal should the pilot see the target in order to land the package on target? So the pilot's looking out the front window. Down below him, he sees the ground. At what angle downward to the ground should he see the target in order to release the package and have that package then land on the target? So our goals for this section is we're going to learn to use vectors to analyze curvilinear motion. We're going to resolve our vectors into our horizontal and our vertical components, and we'll analyze those two problems independently. And we'll then integrate acceleration to find the horizontal distance covered by the package, and we'll use trigonometry to determine the angle theta. So pretty straightforward question, but once again, projectile motion, so we have velocity and position and acceleration in the horizontal and the vertical directions. So no horizontal acceleration, but we do have acceleration in the vertical direction. So let's go ahead and get into the theory for section 1.4. So in 1.4, we define a new term called curvilinear motion, and that's a particle moving in a curved path. We need some more kind of definitions here. So we are going to use, very commonly in this class, we're going to use a position vector r to define the position of a particle p with respect to an origin. And we got a picture here showing that. So if I have an origin of a coordinate system at point O, and I have a point somewhere in that coordinate system p, the position vector r will point from O to p. Okay, so if the particle moves with time, then that vector, that r vector, is then a function of time. So r is going to be a function of time. So the same way that we did for linear motion or rectilinear motion, we are now going to define kind of velocity and acceleration in terms of curvilinear systems. So a more than a one-dimensional system. So we're saying that a position vector r changes with time. So if I have a position vector r at a time of t plus delta t, and then I have a change in r, which is going to be the time or the change in position from t to t plus delta t. So I have initial position r of t, and then at some time delta t later, my position vector points over here. So I have r of t plus delta t. Delta r we are going to define is going to be the change in that position vector, and it will point from our initial point P to our final point P. That's how we define our position vector. And then our average velocity we can then say is going to be our change in position over our change in time, or delta r over delta t. This should look very similar to what we saw in rectilinear systems. Okay? We can then say that we are often in dynamics not interested in an average velocity. We want to know the value of a velocity at an instantaneous point in time. So in this case, we treat it the exact same way. We are going to then take the limit of our change in our vector, our delta r, which we defined here. So r of t plus delta t minus r of t was defined to be our delta r, divided by delta t. We're going to take the limit of delta t as it goes to 0, and we end up with a dr dt. So just like with straight line motion, when we're talking about curvilinear motion, the velocity is going to be the derivative of the position vector with respect to time. So instead of being the derivative of just position with respect to time, now it's the derivative of a position vector with respect to time. We can do that same sort of tactic again with acceleration. So we can say that if velocity is changing with time, if I have a position vector r that points to a point P, and that P has a velocity at that time t, and then at some future time that point P has moved over to a new location, and we have a position vector pointing to that new location, and that point P has a new velocity, at that point in time, I can treat both of these velocity vectors the same way that I treated my position vector. So I can define a change in velocity vector that would then point from our velocity vector at time t to the end of our velocity vector at time t plus delta t, and I can define that to be our change, or our delta v vector. The average acceleration is then going to be delta v divided by delta t. But we are generally interested in an instantaneous acceleration at any given point in time. So we can define the same way. We take the limit as delta t goes to 0, and it turns into a derivative function once again. So our acceleration is the derivative of our velocity vector with respect to time. Acceleration is the derivative of our velocity vector with respect to time. That's the big takeaway from this. Okay, so we are looking at vectors, which everyone should hopefully be really familiar with now from statics. So now we are going to take this kind of theory that we just derived for vectors in general, and we are going to look specifically at Cartesian vectors, or vectors in the rectangular coordinate system. Okay, so if I have a position vector r, and I define that position vector to have 3 components. It has an x component in the I, a y component in the j, and a z component in the k. Please recall that our I is our unit vector that points along the x-axis. So the unit vector has a value of 1 and points along the x-axis. J is our unit vector. It has a value of 2. It points along the y-axis. And K has a value, or a magnitude, of 1 and points along the z-axis. And this is how we define Cartesian coordinates in statics, where we would say we could take a vector, we could break it into its rectangular coordinates, and then we can have some scalar value x, y, and z, and then we utilize the unit vectors to indicate the direction of those components. So I can break my vector component p into components x, y, and z, and I have the directions of each of those components, and if I add all 3 of these vectors together, I end up with my r vector. I end up with my original r vector. So using that, I can then say that the velocity we said was the derivative of our position vector, which we can say is dx dt in the I direction plus dy dt in the j direction is plus dz dt in the k direction. So we would just take the derivative of these values with respect to time, but once again, they point in the I, j, and k directions. So I want to talk about some notation here that's fairly common. You will see this a lot with the subscript, or the accent dot. So the accent dot is often used to indicate a derivative with respect to time. So you probably remember from calculus that a lot of times a apostrophe, or kind of a dash, is used to indicate the derivative with respect to x. It's very common in a lot of engineering courses to indicate a derivative with respect to time by using the dot accent. You will see this a lot in heat transfer and thermodynamics and fluid mechanics, where things are changing with time. You'll see that very commonly. Another way you'll often see this written is we'll use it with subscripts. So we're going to say that v sub x is our velocity in the x direction, v sub y is our velocity in the y direction, v sub z is our velocity in the z direction. So all of these are kind of equivalent. These are just different ways to write, v sub x is equal to dx dt is equal to x dot. So these are all kind of equivalent expressions. They're just written in a different way. So if you see any of these, they all mean the same thing. All right? And so the same way we can do that, we can say that we can take our velocity function and we can then take the derivative of it with respect to time. So acceleration is equal to dv dt. So we can say we can break this Cartesian vector, and we can take the derivative of each of these additions separately. So I have, d of my velocity in the x direction, so the derivative of my velocity in the x direction with respect to time, derivative of the velocity in the y direction with respect to time, derivative of the velocity in the z direction with respect to time. Once again, we can rewrite this a bunch of different ways. I can say that, v sub x with a dot is going to be the derivative with respect to time. More often, you'll see it written like this, in which you'll see x double dot y double dot z double dot, and that double dot indicates the second derivative with respect to time. Okay, the second derivative with respect to time, and you may also see it with the a sub x indicating that the acceleration in the x direction, a sub y acceleration in the y direction, a sub z acceleration in the z sub z direction. So you'll often see it written either in this form here, or you'll see it written in this form here with the x double dot y double dot z double dot. These are both the dot and the double dot are very common tactics used for differential equations. So if you're taking Diff-EQ right now, you probably will see this kind of shorthand regularly throughout the semester. Okay, so for 2D projectile problems, so this is in general, this is anything that we have with the changing acceleration in the x, y, z direction. So we're actually all the way into 3D dimension, or 3D velocities and accelerations, 3D motion, if you will. But we are going to break that down into just 2D projectile problems, because these are very common problems when you have an object that's only being acted on by gravity, traveling through the air, having some sort of position, some sort of velocity. Once again, it's only being acted on by gravity, so it only has acceleration in the negative y direction. Okay, so what we do for this, we can then break. Anytime we have projectile motion or we have 2D motion, we can break the velocity, acceleration, and position. We can break all of these things into components. So I can analyze the x position, x velocity, independently of the y position, y velocity, y acceleration. And we have kind of a picture to kind of indicate what this is doing. So if I have a ball that's going through projectile motion, let's say someone threw this up in the air and the ball travels in a parabola and then it comes back down and it hits the ground here. At any instant in time, you can say, okay, at this instant right here, it has both a horizontal velocity and a vertical velocity. Okay, at any instant in time, it has a vertical velocity and a horizontal velocity. Well, I can now analyze this problem in two parts. I can say that this is the same as taking a ball and throwing it straight up in the air, and then it falls straight back down to the ground. And then I add to that the motion of a ball moving at a constant velocity in the horizontal direction. Once again, constant velocity in the horizontal direction, because we can neglect air drag in these problems. If the problem says you can neglect air drag, we're saying that there is no change in the horizontal velocity because there's no forces acting on this particle in the horizontal direction. However, there is gravitational force acting on this particle in the vertical direction. So we do have a vertical acceleration. So we can then say that for our vertical direction, we can break this down into our three kinematic equations. And I substitute anywhere that we did have an acceleration. So these are our constant acceleration equations. And I just substitute that we have a negative g. So in this case, g would be 32.2 or 9.81, depending on what units you're in. But you're just substituting in a negative g for your acceleration. And these are the exact same as your constant acceleration kinematic equations. Now we have no acceleration in the horizontal direction, so anywhere where there would be a g, you plug in a 0 for that, and we end up with two horizontal direction equations. We end up with the first equation just says that our velocity in the x direction is constant, it does not change. And then we have a second equation which gives us our position as a function of our horizontal velocity. Position as a function of our horizontal velocity. So that's all the theory for this section. So let's go ahead and solve our example problem. Okay, so it was given to us in the problem that the elevation of the airplane is 600 feet. So it is flying 600 feet above the ground and it is flying horizontally. So the position, the vertical position of the plane is constant, it's unchanging. And now we are defining that y is equal to 0 feet is going to be the final position of our package. So the package is starting with the plane at 600 feet. It is going to fall to a final position of 0 feet. Okay, our initial velocity in the y direction is going to be 0 because the pilot is not throwing the package downward. He is just releasing the package and letting it fall. So it has an initial vertical velocity of 0 feet. We are also defining our initial horizontal position, x naught here, as 0 feet. So we are saying that we are defining our coordinate system as kind of shown here. So we are defining our coordinate system as x is equal to 0 at the time that the pilot releases the package. Our horizontal position, or our horizontal velocity is constant. It's unchanging. It's 176 feet per second, which was given to us as the velocity of the plane. And once again, we're going to define that our initial time is 0 seconds. And once again, that initial time is when the pilot releases the package. So we are defining initial time as 0, pilot releasing the package, initial horizontal position at that time is equal to 0 is at 0 feet. So this is how we are defining our coordinate system. So the question is, what angle theta must the pilot see to see the target to release? So we're looking for the angle theta that the pilot is looking down out of his windshield and where he sees the target, and he knows at that point he needs to push the button, drop the package, and it will fall to the target. Okay? So we said that our horizontal direction we can analyze first. So we said we can analyze these problems by separating the horizontal and vertical components into 2 individual problems and then combining them together at the end. So we are going to start with our horizontal direction. Because we are neglecting drag force, there is no force acting on the package in the horizontal direction, so our acceleration in the x direction is equal to 0. We can then integrate that. We can integrate that problem. So x double prime, this is the same as dv x dt. So dv sub x dt, I multiply my dt through, I integrate this equation. Now I'm integrating from some initial velocity to some final velocity, and I'm integrating from some initial time to some final time. But remember that this is 0. Since a sub x is 0, the entire right side of this equation becomes 0, and now I integrate dv just becomes a v, and I evaluate that v at v sub x and v naught sub x, so I end up getting that difference is just that my velocity in the x direction is equal to a constant velocity, is equal to my initial velocity of 176 feet per second squared. So we were able to derive that relationship that our horizontal velocity is always constant. It is not changing because there is no force acting on the package in the x direction. Okay, once again, I can integrate this equation. I'm integrating from some initial position to some final position, and I'm integrating v sub x dt from some initial time to some final time, and I derive that same equation that we just saw. I derive that we have some change in horizontal position is equal to our velocity in the x direction times some change in time. So I can say that x sub t, because I've defined v naught to be equal to 0, and I define t naught is equal to 0, my position as a function of time is simply 176t. 176t. So I can do the exact same thing in the vertical direction. So I can say that my acceleration, I can fix that, my acceleration in the y direction is equal to y double dot, which is the same thing as dv sub y dt. So I multiply my dt through. I can then integrate from some initial velocity in the y direction to some final velocity in the y direction. And sorry about that. This should be a dv dy, or dv sub y. And then I am once again integrating from some initial time to some final time of my acceleration in the y direction dt. Now we know what our acceleration in the y direction is. It is a value of negative g. It is constant, so it can actually get pulled outside of this integral. So now I'm just integrating dt from t naught to t, which I then evaluate is just a t minus a t naught, where this negative g was my acceleration in the y direction I then pulled out. And this just becomes a v sub y as being evaluated at initial velocity and a final velocity, and I end up with this standard equation here. Now we have to take into account our boundary conditions, or our initial conditions. We said that our initial velocity in the y direction was 0, and we said that t naught was equal to 0. So our velocity in the y direction simply becomes v sub y as a function of time is equal to negative gt, So this equation simplifies to just once again, a linear equation, which is what we expected it to become. We can then integrate this equation or this relationship here. So we can say that the velocity in the y direction is dy dt. I can kind of multiply my dt through. I can integrate this and evaluate at different times. So I'm integrating from y naught to y of dy, and then I'm integrating from some initial time to some final time at negative gt, and that becomes that y minus y naught minus 1/2 g, because once again, negative g is a constant, so it can get pulled out of this equation. T becomes 1/2 t squared. 1/2 t squared evaluated at t and t naught becomes negative 1/2 g t minus t naught squared. So I take this equation that I just derived and I can plug in my boundary conditions. I know that my initial position is at 600 feet, and I know that my t naught I define to be equal to 0. So my y sub t, my vertical position equation, becomes 600 minus 1/2 gt squared. So now I have both my horizontal position as a function of time and my vertical position as a function of time. So now I can use these together, and I can say when the package hits the ground that its final position, its y position, is going to be 0. So I can then use my vertical position equation to solve for the time that it'll take for that package to fall that 600 feet and hit the ground. So I do that, and I say, okay, my final position is going to be 0, is 600 minus 1 or 0.5 or 1/2, 32.2 t squared. I then solve for t from this just using basic algebra, and I get that t is equal to 6.105 seconds. T is equal to 6.105 seconds. I now know what the time is it takes for that package to fall from 600 feet and hit the ground. I can plug that time into my horizontal position equation, and I can determine that x of t, I'm saying that t now is 6.105, is 176 times 6.105. If you do that multiplication, I figure out that it travels 174 feet. 1,074 feet. 1,074 feet. So now I know how far it travels horizontally in the same time it takes for it to fall 600 feet. So I can just draw myself a triangle. And it takes, in the time it takes to fall 600 feet, it then travels 1,074 feet. I can say that opposite angles across two parallels. So I draw a parallel line here. If this is my theta, this is also my theta. And so I can immediately see that my theta is the tan inverse of 600 divided by 1074. So my theta becomes 29.18 degrees. So when the pilot looking out of his airplane and he sees the target downwards at an angle of 29 degrees, he can release the package, and that package should land right on top of the target. Okay, so that's the solution to our 1.4 case study. Let's go ahead and work another couple examples for each of these sections. So the first one, let's do another 1.3 additional example. We have a spring-loaded machine is able to launch a 2-kilogram disc 50 meters vertically into the air before it begins to descend. What is the initial velocity? So we have a spring-loaded kind of launcher here, and it launches this disc up in the air. It goes up 50 meters, and then all of a sudden it stops, and then it falls back to the ground. Okay, so the big takeaway from problems like this is we have to recall that when something is undergoing only vertical motion and the only force acting on it is gravity, at the apex of that motion, the velocity is 0, right? So it gets launched, it has some initial velocity up, but it's slowing down. At some point, for one instant, that velocity stops and is 0. And then it starts to fall back down to the ground, and the velocity is negative. So because we know at the apex that our velocity is 0, we can use our velocity position equation. So we can say that our velocity is going to be 0, our velocity at the apex is going to be 0, and we know that v naught is what we're after, so that's our initial velocity squared, plus 2 times our constant gravity, or our constant acceleration due to gravity is negative 9.81 meters per second squared, and we know that at the apex it is at a position of 50 meters, and it initially was at 0 meters. So we defined our datum as right here where the disc was originally. So it was originally at 0 meters, and it travels up to a distance of 50 meters. So this just becomes an algebra problem, and I end up getting that V naught is the square root of 981, or it's 31.32 meters per second. 31.32 meters per second. Once again, this is a scalar equation. I had to determine whether that 31.32 was positive or negative, and we know the launcher did not launch the disc downward, so we're saying our initial velocity is positive or upwards. We had to interpret that from the problem. Okay, let's do a little bit more complicated problem for 1.4. So once again, we're kind of back into 2D projectile motion. So in this problem, we have a small ball is thrown up a slope a distance of 30 feet. So note that this 30 feet is a distance up the slope. It's not a horizontal distance, it's not a vertical distance. It's how far you would actually have to walk up the slope to pick this ball up. The slope is at a 30-degree angle from the horizontal, and the ball's initial velocity is 40 degrees from the vertical. So we have our 30-degree angle on the slope from the horizontal, and the ball's initial velocity was 40 degrees from the vertical. So the ball leaves the person's hand 5 feet from the ground. What is the initial velocity? What is the initial velocity? So we're saying this is a 2D problem. So once again, we are going to split this up into vertical and horizontal components. We will solve these separately and then combine them at the end to get our answer. So for a 2D problem, we know that these are our position equations for projectile motion. These are our position equations for projectile motion. These are our constant acceleration equations, where acceleration is negative g. Acceleration is negative g. So the big thing that we need to remember here is that V naught, our initial velocity, is 40 degrees with the vertical. So because the 40 degrees was given with the vertical, we know that our opposite from this angle, which is a sine is opposite over hypotenuse. The opposite side of the triangle from this angle is going to be this here, which is going to be our horizontal velocity. So in this case, our horizontal velocity is our initial velocity sine of 40. Our initial vertical velocity is going to be our initial vertical velocity is going to be our total initial velocity cosine of 40. So because our angle was given with the vertical, our sines and cosines are swapped from how we're used to normally seeing it. And then we can then plug these equations here, these values for our initial vertical and horizontal velocity, into our position equations, and we get these equations right here. So I just plugged in our initial vertical velocity is V naught cosine 40. Our initial horizontal velocity is V naught sine 40. We just plugged them into these equations. So next we need to find the x and y locations, the final locations where the ball lands. So we said that the ball lands 30 feet up the slope. 30 feet up the slope, so we need to make sure that we are clear with where we define our coordinate system, or where we define our datum. So we are going to define our datum here at the base of the slope. So right here at the base of the slope, we're going to have x is equal to 0 and y is equal to 0. If that's the case, then my y position is going to be 30 sine of 30, because once again our slope angle is with the horizontal. So our y position is going to be 30 sine of 30, and our y position is going to be 30 sine of 30, and our x position is going to be 30 cosine of 30, like this. So we plug all that in, and we get that our final position of the ball is going to be at 15 feet in the y and 25.98 feet in the x. Now, depending or based off of where we defined our coordinate system, we said we initially threw that ball from 5 feet in the air. So it has an initial x position of 0 and an initial y position of 5. Okay, so now we have our initial and final conditions. So we have, at some time t, our y is going to be 15, and at some time t, our x is going to be 25.98. At time is equal to 0, our x is going to be 0, and at y is equal to, or t is equal to 0, our initial y is going to be equal to 5 feet. Okay, so we're going to use these equations that we derived before, and we can now say that our final position is going to be at 15 feet plus our initial position, which is going to be at 5. So once again, we're looking in the vertical right now, plus our initial vertical velocity at some time t minus 1/2 gt squared. So this is our vertical position equation, and we can do the exact same thing with our horizontal position equation. And so we have a 25.98 is our final x location. Our initial x location was 0. We have some initial velocity, sine 40, as our initial horizontal velocity, and some time t. So now what we have is we've taken those position equations, our vertical position and our horizontal position, and we have two equations with two unknowns. We don't know what t is, and we don't know what v naught is. So now we have to solve this system of equations. So because I have a quadratic equation with t here, I'm going to go ahead and solve my horizontal equation first. So I'm going to solve my horizontal x equation for v naught, and I find out that v naught is equal to 25.98 divided by t sine 40. I can now take that and I can plug that v naught into my position equation in the vertical direction. I plug that in and I end up getting that 25.98. I had a t on the bottom of a fraction here. I have a t on the top of a fraction here, so my t's cancel out. I end up with a sine 40 on the bottom of a fraction here. I have a cosine 40 on the top of a fraction here. That turns into a tan 40 on the bottom of a fraction. So I end up with 10 times 25.98 divided by the tangent of 40 minus 16.1 t squared. Now I can just solve this using algebra for t. And I solve that, and I find that the time that the ball then lands up here on the slope is 1.141 seconds. So I don't know what the initial velocity is, but I know that it takes 1.141 seconds to land. I can then plug that back into my x velocity equation. So now that I know what my time is, I can find that v naught is equal to 25.98 divided by 1.141 sine 40. Once again, that was what we solved for v naught using our x position equation, and I can say that my initial velocity is 35.42 feet per second. So this problem simplified into a system of two equations with two unknowns, and we had to solve for those two unknowns. So with 1.3 and 1.4 covered, we are going to stay on schedule as kind of shown in the Blackboard course schedule. So for Thursday, you need to read 1.5 and 1.6. Be prepared to take a 1.5, 1.6 reading quiz at the beginning of class on Thursday.